And this is a research presentation of Christine mapping the brain network microstructure using quantitative MRI.
Okay. All right. I think this works. Okay.
Yeah.
Okay. So we're going to be building on what we talked about this morning. Before I jump into the talk, I just want to, maybe tell you a little bit about why we're trying to bridge, the gap between quantitative MRI and network neuroscience. So you may or may not be aware that myelin plays many roles in the brain, right? And that it's not as static as we originally thought. So myelin is really dynamic, right? It's an additional form of plasticity. And we know that, of course, the myelination of our brain, develops a lot during our first years of life, right? There's this steep gradient of myelination, but it also remains dynamic throughout the entire lifespan. So you can use this as a form of plasticity, even as an adult, okay? And it plays several roles. So not only, of course, accelerating, the propagation of action potentials along the axon, but also like fine-tuning the arrival times, right, in these networks. So it plays a role in synchronization of function in your networks, okay? And in the cortex, actually it plays a really important role as well, because I shouldn't say the majority, but more than half of the myelin in the cortex is actually ensheathing inhibitory interneurons. Okay, so it's been shown in some different neurodevelopmental and mental health disorders that a loss of myelin in the cortical sheath can actually impact your excitatory inhibitory balance. Okay, so all this to say that myelin plays a huge role in modulating whole brain function, right? And it's becoming, quantitative MRI techniques, as I showed in the earlier talk, are becoming more and more used by the community. And I'm really excited to see it being used by the network neuroscience community, where they're starting to integrate these measures in their structural network models. But I have some concerns because I think we can do better, okay? We need to adapt our techniques for that specific application. And so that's what I'm going to be showing today, how we have been, developing advanced MRI techniques for the specific purpose of, mapping the microstructure of the brain connectome. Okay. Oops, this should work. All right. I can skip over this. Okay, so annotated brain networks. So I'm assuming most of you are familiar with this typical network representation of the brain, right? Where you have nodes that represent, group populations of neurons in gray matter structures, and then you'll have edges, which represent the, groups of myelinated axons that connect these nodes within the network, right? So there's, a few, an increasing amount of literature that use MRI, right, to annotate the nodes and the edges in these networks. So some of the more common features that you'll see used, for example, for nodes, you'll see people annotate the nodes by the thickness or volume of the node, right? The surface area, T1 weighted over T2 weighted signal ratio, T1 time, mean diffusivity, etc. So most of these features can be extracted from, public data sets like UK Biobank, HCP, and a few other ones. So I think this is a great start. It's really interesting. I think we can do better, especially with regards to myelination. So here are a few directions that my lab has been working on. Just in case you're interested in it, it's not actually what I'll be talking about today. So we've been working on developing high resolution techniques. Most of this is done at 7 Tesla in order to really map the microstructure of these cortical nodes. So one of the techniques that my postdoc, Christopher Rowley, has been working on, he's now faculty, just opened his lab at McMaster University and is probably recruiting. He's a fantastic person to work with. He's been doing work on a relatively new contrast mechanism, actually, which has been worked on a bit in the United States, and actually some of the French labs are champions in this, is inhomogeneous magnetization transfer, okay? So the idea here is that it builds on the concept of magnetization transfer, but you're more specific to the myelin, the macromolecules that form the myelin sheath due to the architecture of that sheath. Okay, so this is critical in my opinion for the cortex because it really improves your specificity to myelin in a structure where you have a lot less myelin. Okay, so it's really important. Another direction that we've been going on at 7T, this is done by my PhD student Sajad Faizola, who's been working on very high resolution diffusion imaging so we can start to capture the microstructural features of the cortex. So for this, it's challenging. We have to use non-Cartesian imaging, and we're also using advanced diffusion encoding techniques. So I think with Max, we've looked at a lot of linear encoding, right? So you encode diffusion of the spins along the x-axis, the y-axis, the z-axis. Well, here we're doing what we call tensor encoding. So we're encoding diffusion within planes or within spheres. And this allows us to tease apart the macroscopic geometry from the microscopic geometry. And so it allows us to go from maps of, for example, FA to micro FA. That's really telling you about the microscopic fractional anisotropy of your tissue. So I won't be saying any more about this, but if you're interested in it, I'd be happy to talk to you about it further. It's really some of the techniques we're working on to improve our characterizations of the nodes in the network. Today, I'm actually going to focus on the edges, on the white matter tracts, because I think this builds nicely on the work that was presented earlier in the week by Maxime Descoteaux. Okay, so here are the common, features that you will extract from your diffusion data and your tractography. So you guys have, Max presented tractography and everything earlier this week, right? Yes, thank you. Okay, so first of all, you'll determine, well, is there actually a connection between two nodes in the network? Hopefully, you're right. Then, okay, what is the strength or the caliber of that connection? There's different ways to go about this. Historically, we would do the number of streamlines, although there's a lot of confounds with that. We can also look at the length, right? The geodesic length of that connection, the mean diffusivity, fractional anisotropy. These are all diffusion features that you can map onto those structures. And then you can, if you have other modalities, other maps from MR, you can map your T1 time, your MT, for example, onto those tracks as well. Okay. So the idea here is that we really want to build on this and extract as many features as possible to comprehensively describe the microstructure of these tracks, which will affect the function in the network. Okay. So most of these, tract features we're extracting using a pipeline that we call tractometry. Okay, so there are a few different flavors to this, but this is the way we do it in my lab, and I think it describes the general concept. Okay, so I'll just walk you through it. The first step, of course, is to make sure that your diffusion data and your quantitative MRI maps, whatever you choose those to be, are perfectly co-aligned. That already can be a bit of a challenge, right? Because they may have different distortions in them. So the top here, we have the streamlines, and the bottom are MT map. Once they're nicely aligned, we can then, project the data onto the reconstructed streamlines. So here I just have a subset of streamlines for visualization, right? In blue, we mainly have our cortical spinal tract. We have a few going through the corpus callosum in red. Where the color here is really just describing orientation. So now we're going to project onto them the MT sat values. Okay, so I'm just projecting them in color map, in a spectral color map here, so you see the variation. The next step is to take the mean or the median along a streamline. So you have a single value associated to each streamline, shown here. And then finally, we'll, identify all the streamlines that connect two nodes in the network. And we'll take the average or the median, whatever you like, across those streamlines. And that becomes the value that we annotate the edge with, right? So here you kind of have a visual of your network. And this is the connectivity matrix, as you guys are familiar with seeing. And these are what we'll call QMRI annotated. I know a lot of people say weighted, like MT weighted, T1 weighted connectome. I avoid using the word weighted because it reminds me of conventional MRI contrast, okay? So I say annotated, okay? So it's really just information that you're adding to the network, okay? And so you can, people have used this technique to study the brain in general and done amazing things. So this is work actually by Bogdan Dragansky's group in Lausanne, where they scanned, a bunch of participants between the age of roughly 10 and 80 years old to look at, healthy neurodevelopment and late age development. And what's interesting is that you can see, well, here I'm only looking at 2 tracts. They looked at like 30 or something, but the shape of the curves vary between the different tracts in the brain. So, they'll develop at different rates and heat their peak at different ages, right? And that's reflected in the development of different skills, right, in children. But they also have different shapes depending on the contrast that you're looking at, right? So not all of those features develop at the same time. So this is kind of more of a classic tractometry view. Now we can do similar things looking at the connectome. So here's just an example of all the different types of features that we can extract. So the same list as earlier. This is just your typical functional connectivity matrix, where in red I've kind of outlined the canonical resting state networks, okay? So same structure for all the subsequent ones. First 3 here are really measures of tract caliber or strength, connection strength. So NOS is just there for historical purposes, for comparison. But SIF2 and commit, which is what we work with the most, are really more accurate measures of tract caliber, okay? It's just that are extracted from multi-shell diffusion data. And then a few other features that are really just projected, as I showed earlier, onto these tracts. So R1, neurite density, FA, fractional anisotropy, radial diffusivity, and length of streamlines. Okay, so we really have a rich data set here that we can start to analyze and start to look at the relationship between the different features, right? So, for example, here, this is a group of like healthy adults, okay? And we're starting to look at, for example, the relationship between R1, which is correlated with myelin content. Here we're looking at healthy controls, so no major pathological confounds, right? And you'll see that for the short caliber connections, which are shown here in red, the R1 is inversely correlated with edge caliber. It's kind of interesting, not necessarily what we'd expected at first. And we can also see that once you correct for edge length, R1 is negatively correlated with functional connectivity. Again, not necessarily what we would have expected, but this has been replicated by at least 2 other groups. So the major interesting results. Take it all with a grain of salt, okay? Because for example, these techniques have also been used in not only to look at healthy development, but to look at schizophrenia, to look at cognitive training and how this impacts the myelination of tracts and maybe their function, right? Really interesting study. But all of these studies have the same major limitation, which is the macroscopic wiring geometry of the brain. It causes partial volume effects. So this is work by Urisin, right? And what you see here is that the voxels in red have one main fiber orientation. All the others have 2 or more, okay? So basically this means that in 60–90% of the voxels in the white matter at current imaging resolutions, you have more than 1 fiber population at different orientations, right? But you only have 1 MT or R1 or T2 star metric in that voxel. So you have this partial voluming effect. And then you're sampling that value along the entire length of your tract. So it's like this massive blurring kernel that's being applied to your data and to your annotated connectome, right? So I'm just going to give you 2 concrete examples here of what will happen. Here we're looking at FA, right? So fractional anisotropy derived from diffusion data. To give you an idea, when you have a single fiber population, your diffusion tensor will look more like this, like towards a more elongated stick-like structure. The FA will be high, right? If you're in CSF, where the diffusion is, happening in all the different directions, it'll be a sphere, so your FA will be 0. Okay. 1 fiber population, FA 7. As soon as you're in a voxel where you have 2 fibers crossing, your FA will dive down, right, to like 0.2. So what we see here, this is work by Sylvia DeSantis and Derek Jones' group. They're basically projecting the FA onto a bunch of different reconstructed tracts in the brain. And you can see how that FA varies, and dips to really low values in areas where those tracts are crossing or kissing another tract in the brain. So you're capturing here is, again, macroscopic geometry. You're not really capturing the microstructure of the tract, which is what you're hoping to get with your FA, right? So that's what happens in the context of FA. It's a little bit different when you're talking about T1 or MT or things like that, right? What's going to happen is that here you have, again, the T1 single fiber, no problem. In a voxel where you have two tracts crossing and that they have different T1 relaxation times, okay? The value in the voxel will basically be the average, the weighted average, right, of the T1 of both tracts. Something, not exactly that, but roughly, okay? So what you end up having is, like, again, this kind of a blurring effect, right? All the T1 times are going to look similar. They're all going to converge towards a similar value. So our issue really is one of partial volume effects along the tracts due to the macroscopic geometry of the brain. So today I'm going to present two techniques where the purpose, joint purpose of both of them is to really disentangle the MR properties of the individual white matter tracts in the brain. So effectively, my daughter really liked this image, so I put it in there. You're trying to recover the color of each spaghetti, because right now they're all looking brown, okay? So that's what we're trying to do. And the strategy we're going to use is one of multi-encoding. So building on that last example that I showed you in the previous talk, where we talked about diffusion relaxometry, we're building on that, okay? So we're going to co-encode in the same acquisition, two different contrast mechanisms to really try to disentangle the microstructure features of all the tracts that are kissing and crossing in the brain. Okay. So the first approach that we're going to talk about is tract-specific, or rather orientation-specific T1 mapping, okay? So this is what we're doing right now. This is our goal, okay? Right now, using diffusion, you can represent two tracts that are crossing in a voxel using two pixels, right? Where a pixel is a fiber element within a given voxel. So for those of you who are familiar with MR tricks, for example, they use the pixel notation, right? So what we want to do is we want to associate a T1 value to each pixel in a voxel, right? That's the goal. So we're going to do this, as I said, using multi-encoding. So when we do conventional multimodal imaging, what we do is we're basically varying the contrast separately, right? So first you'd vary your T1 contrast, and then use all of that data together to calculate a T1 map. And then you'd vary your diffusion contrast, right, in different diffusion encoding directions in order to reconstruct the fiber orientation distribution function within a voxel. So it's kind of like acquired separately, processed separately. And at the end, you try to merge everything together. We're going to do the opposite. We're going to basically acquire this whole 2D plane of information. So it's as if we were doing a T1 relaxometry experiment for each diffusion encoding direction. Now, if you recall from Maxime's talk, if you encode diffusion along X, all the spins that are like moving along X, the signal from those spins will be dephased. It's gone. So really, what you're capturing is the information from all the other diffusion directions, right? So that's what you're getting here. So you really need to combine all of this information together and fit it to an equation in order to extract T1 relaxation times specific to different orientations. Okay, so how do we do that? A little bit about the acquisition here. So in order to do T1 mapping, we typically do an inversion recovery scan. So this maybe answers some of the questions that we had during the coffee break. So we start with an inversion preparation pulse, 180 degrees. Okay, it just flips your magnetization along Z. You have nothing in the transverse plane. You let that signal recover. After different inversion times, you apply a second pulse, a 9-degree pulse, that brings your signal into the transverse plane and you acquire it, right? So this whole process needs to be repeated for different TIs. These are your resulting images, right? And so you see that you basically can then fit those data points to a curve and you get your T1 value at every voxel. This is what your typical diffusion sequence looks like. Oops. Right? So a spin-echo experiment. In blue, we have the diffusion encoding gradients. Of course, they're applied along the different axes, right? Depending on the direction that you want to encode your diffusion in. Okay. And so here, for example, if you're encoding along the X direction, you'll see that you get signal loss in the corpus callosum along that direction. So here are just 3 different examples of directions. What we're going to do is we're basically going to merge these. It sounds simple. It's actually a little more complex to implement, but basically apply an inversion pulse. We're going to vary this delay between the inversion pulse and the 9-degree pulse like we did before, but we're going to just run the diffusion experiment right away. So this whole process is repeated several times. And an important point here is I'm getting an error message. So just let me know if ever it doesn't work on the, okay. So an important point here is that you don't want to use a B value. You don't want to encode diffusion too strongly, because or else you'll lose all of the signal from your extracellular space, right? You want to be working in a regime where you have signal that's coming from the intra and extracellular space, so that you're really getting your T1 of your entire fiber. An important point that I want to make here is that, of course, we're starting with our equilibrium magnetization, right? And then the only way to encode contrast in an image is to remove signal, right? So you remove signal using diffusion to create contrast, because you can't go higher than your equilibrium magnetization. And then you lose signal again by doing an inversion recovery experiment. So the challenge in a lot of these multi-encoding sequences is that you're working at much lower signal to noise ratios, okay? And longer acquisition sequences. I think you're... Ouais, je pense parce que la connexion est comme pas... Ouais, elle n'est pas stable. Ça doit être l'erreur que j'avais.
Ouais, là, vous êtes parti du bon.
Ouais.
Sinon, vous pouvez tester le véhicule avec vous venez d'école. Il y a du roi marche.
Ah.
Ah, ça y est, là, je vous vois.
Ouais. OK, on reçait juste le partage d'écran.
Okay.
C'est beau? Okay. So this is your signal equation for a single fiber. This is like the Centre de Recherche Mathématiques. So I figure it's fair to put a few signal equations in the presentation, you know? So it's not complicated. This is basically your inversion recovery experiment, right? So S naught is like M naught. It's your equilibrium magnetite like signal. And then you have a function that's, you know, your T1 decay. So it's a function of your T1, your repetition time, okay? And of course, your inversion time, which you're varying, okay? So this will allow you to get a measure of T1. And then, of course, you multiply that by the exponential that describes your diffusion encoding, okay? This is for a single fiber. If we have multiple fibers in a voxel, similar to the multiple compartments in a voxel, we are going to assume that we're in the slow exchange regime, okay? And so those spins are not really exchanging during the time course of our experiment from one fiber to another. And so you can simply then characterize it as the sum of the signals coming from each compartment, right? Depending on their fiber volume fraction, so the fraction of the voxel that they occupy, okay? And then you'll have one T1 per fiber and one diffusivity per fiber. So that's all we're doing. Sounds simple. You can effectively fit the whole diffusion part using a multi-shell diffusion experiment, but you need the inversion recovery part to get those fiber-specific T1s. Okay, so this is an example of what the data actually looks like. So this is what I showed you earlier. So with no diffusion encoding, you get that T1 experiment. And this is where we add a diffusion encoding along the left-right direction. We're at a b-value of 1,000. As I said, we don't want to go too high in terms of our b-values for this type of experiment. And this is what the data looks like. So dash points is the data, the fit is in the solid lines for a voxel in the corpus callosum. So your fiber direction is X direction, right? Which is why the signal will be lowest when you're encoding diffusion along the X direction. But otherwise, you see that you have this nice signal recovery that we're fitting nicely. So that's more of a like just checking that everything works because we have a single fiber, obviously, in the corpus callosum. But we're going to start to look at some other more complex areas. So this idea was not really introduced by my lab. It was actually introduced by Sylvia DeSantis, who's working with Derek Jones at the time. And so they did this at 7T within a smaller slab in their original work. And here's data averaged over 7 subjects for a few different tracts. And what you really see is that, you know, in red, we have the new technique with the dual encoding. Not only do they really reduce the variability across their subjects, you know, which may be due to the fact that they actually have more data to fit to. But what's interesting is that there's all these areas where the two values really deviate, right? And that's systematic, like that's like across the 7 subjects, right? And I think that what's happening there is simply that in the MP2 range, so in the pure T1 mapping method, you're getting contributions from the crossing fibers, which in this case we're removing, right? So that's why your T1 value in a tract is much more consistent along the entire length of the tract using the dual encoding technique as opposed to the original T1 tractometry technique, okay? So really a nice original contribution that shows the potential of this work. The issue is that for like a slab that covered about half the brain, it took them basically like over an hour to acquire. So this isn't, they're not going very far with this. It's a proof of concept that was really beautiful. So we really wanted to bring this further, move this further. And so we started working on this and teamed up actually with John Panimetti's lab in Boston in order to accelerate the scan. So we did this by using a technique called slice shuffling. So instead of repeating, you know, the inversion recovery experiment each time, what we do is we have an inversion time, and then we scan, we acquire all of the slices back to back. So every slice here will see a different inversion time, right? When we repeat the sequence, we simply shuffle the order in which the slices are acquired, okay? And so they now have a different inversion time in the second acquisition. But it means that as a whole, it really accelerates our multi-encoding acquisition technique, right? So we implemented this at 3T, and we're now able to do the entire brain in 13 minutes. Because every slice sees a different inversion time, it is normal that you see this stripy artifact, right? It's completely normal because you have basically this T1 recovery that's happening while you're acquiring the images. And in diffusion imaging, in case you didn't know, we tend to do all of the even slices, then we go back and we do all the odd ones. So that's why you have this stripy artifact. And there's actually a group in the UK that developed a similar sequence. And because of this, they call their sequence Zebra. So we were talking previously about validation. Sometimes we have to be a little creative in our validation techniques. So this is actually a master's project in my lab. It was really fun, where we wanted to see, are we really able to disentangle the T1 times of the fibers? And how are you going to do that in the brain? It's really difficult because they're always crossing. It's really hard to find extended areas where you have a single fiber, right? So we decided to use asparagus, and similar to that celery experiment that you did as a kid, where you put celery into like food dye and it like soaked up the pink or the blue. Well, we did this with asparagus. We put it in solutions with different concentrations of gadolinium. And gadolinium will basically change the T1 relaxation times of your solution, okay? So now we have asparagus, which are kind of fibrous. So you'll get the diffusion, right? That are crossing at 90 degrees, and they all have different T1 times. And we're just zooming in here on the crossing of 2 asparagus, okay? And so what you see, the little bars, you know, they're not perfect, and it's because they're actually demonstrating the main orientation of diffusion that was extracted from our diffusion data. And then in blue, we're showing the T1 times, right? And so you can really see this continuity where the horizontal asparagus is like in blue, right? And so you can see that in the crossings, you really maintain that value. And the vertical horizontal asparagus has red, so corresponding to much higher T1 times. And so just in case you're concerned that it wasn't a clean fit, we actually have a nice fit here to the data. So we basically, our starting point will be the average T1 of the voxel, and then we fit it to the signal equation with the diffusion, and we really get a nice single minima there. So it is a clean fit. There's no you know, uncertainty in terms of multiple minimas. Okay, so what does this look like in the human brain? I have a few examples. This is one of my favorites, where you really, at the front here, where you have the corpus callosum that's kind of like going down, and then you have the and then you have the cingulum. And you once again can really see the difference in T1 times just at this boundary, you know, where you have voxels that include both fiber populations, okay? So there's this area, and then another area where we can see a nice crossing where you also see the fibers alone in their neighboring voxels. I'll get to that in a minute, right here. So similar, we're kind of changing our representation here. So the color scheme here represents the main orientation of your fibers, right? So blue head foot, red left right, green and plain. And here the sticks, their grayscale represents their T1 time. So we're much lower here where the cortical spinal tract is crossing the pontine fibers that are going left to right. And it's actually the pontine fibers that tend to be more densely myelinated and therefore have a lower T1 time. And we're able to capture that nicely in our data. Okay, so this is just projecting it onto the tracts, the total reconstructed tracts. So of course you just, you know, what I find is really nice is that you get this better continuity along the tracks. This data does look a little noisy speckly because here we're not doing any averaging, you know, along tracks or across voxels. It's really just a clear projection of the fixal T1s onto the streamlines. Okay. So I think what's really exciting about this is that, you know, we're able to now get more than one T1 estimate per voxel, right? So we have one per pixel in the voxel. The strength here is that you can now project this data along a streamline and actually see whether the T1 value varies along the streamline, because you're actually resolving this problem at the voxel level, right? So in cases where you may have a lesion and you want to know if the tract that goes through that lesion is affected further away from it, it could be an interesting technique to use. So there's strengths there. But one of the limitations is that what happens if you have, sorry, I'm going the wrong direction, 2 fibers that are actually parallel in a voxel. I can't do much about that. Not if I'm working at the voxel level, because they'll be represented by the same pixel, all right? So this is one of the limitations of the technique. I'm also going to say, just full transparency, because these techniques we make them available. They're implemented on Siemens scanners at 3T. Anyone can use them. We're happy to share them. But this sequence implementation, due to the shuffling and everything, is a little more complex, right? We've optimized it for whole brain. The post-processing, you know, pipeline needs to be adapted to it because the images are zebra-ish, right? They look a little different. So it does take, there is a, you know, it's not out of the box. There's a little bit of work that needs to be done there to customize pipelines to this type of data, okay? So these were the 2 things that were bothering us. The fact that it was a little more complex and that we couldn't deal with parallel fibers in a voxel. And so this encouraged us to work on the second technique, where we're combining MT with diffusion. So really similar context, problem, but we're going to go about it in a different way. Instead of solving things at the voxel level, we're going to work on a global optimization, a global solution, okay? Oh, I don't know why only half of this appears. So again, just resuming the problem here. Imagine this is your ground truth, that you have two fibers that are crossing, that the myelin volume of the first fiber is 0.1 and the second fiber is 0.3, and that it's consistent along the entire length of the fiber. If you were to take that and represent it using MR, what you get is two reconstructed streamlines and a myelin map, which basically looks at the total myelin amount in the voxel. And so it would be this is what it would look like. So then if you did conventional tractometry and you project this back onto the streamlines, this is what you would measure. We know this, right? So you're getting the wrong values. This is what MR tractometry does. So now we're going to do things again a little differently, but we're going to keep this assumption that the feature, in this case, the MT of the tract is the same along its entire length, okay? And the previous work that I showed by Sylvia DeSantis on T1 kind of highlighted that, right? That these features are consistent. You won't have a drastic change in myelination halfway through a white matter tract in the healthy brain. Okay. So again, a bit on the sequence programming for those interested in this. This again is your basic diffusion sequence, and we are now adding MT. So in this case, our MT prep area is a little bit different. Instead of having a single off-resonance pulse, just to get maximal MT contrast, our simulations showed that we should do a whole series of off-resonance pulses. I think they're about 4K off-resonance. And so we acquire the sequence twice. Once without MT, so a normal diffusion sequence, and once with MT. And again, the only way to encode contrast is to remove signal. So you always have a drop in signal as soon as you encode your second contrast mechanism, right? Now, if you take the spherical mean, by this I mean you're just averaging all of the images across the different diffusion encoding directions, you'll get something that looks like this, right? And then you can simply combine those to create a simple MTR map. So this is just to show you that we actually do have decent MTR contrast, even when we include it with the diffusion sequence, okay? But that's not how we're going to analyze the data. There's a few tricks here in terms of improving your MT contrast. When we do MT, we're usually working with a gradient echo sequence, a small flip angle. So almost all of the energy that you're depositing into the brain comes from your off-resonance pulse, right? There are safety limits in terms of how much energy you can deposit into the brain. You don't want to heat your tissue, right? And so when you're doing diffusion imaging, you have a spin echo sequence. That's a lot of 90 and 180-degree flip angles. They deposit energy in your brain. If for those, you're doing multi-band acceleration, then you're also increasing your energy deposition because you're effectively exciting multiple slices at once, right? And then if you're doing fat saturation, again, that's another way that you're putting energy in. So our concern was that in the diffusion sequence, you're already putting so much energy into the brain just for diffusion that how much do we have left to create our MT contrast? Not very much. So we've tried to reduce that, remove multiband, use an alternate way to do fat saturation and things like that in order to generate the largest MT contrast that we could. So this is what we were working on here, and really, as you can see, improved the MT contrast and signal to noise ratio quite significantly by doing that. Now, this is the tricky part. We only have two measurements, MT on, MT off. Not really enough data to do a complex, fitting at the voxel level. So we teamed up with Alessandro De Ducci's group in Verona, Italy. They had developed the commit framework, okay? This was done to basically improve the estimates of tract caliber in tractometry, okay? But the idea here is that it's a global optimization approach. So again, here I think he's still using a stick Zeppelin ball model, okay? Except that you have a ball at every voxel that represents your CSF. This is for diffusion. You have a Zeppelin at every voxel, which represents your extracellular space. You have a stick for every streamline, because it should be consistent along the streamline throughout the entire brain. So now every measurement, right, at every voxel becomes an equation that sums up the contribution of all of these. And you can solve that over the entire brain and then find out what is the contribution of the stick fraction for every streamline that you have. Okay, so it's just a massive set of linear equations, but it means that you have to apply it to the whole brain. You can't do just a part of it, right? Your data quality has to be good in the whole brain. If you have an artifact somewhere, it'll affect all of the results, right? Okay, but you end up with this improved specificity of having that stick fraction that is streamline specific. Again, you're making the assumption, which is valid in the healthy brain and in some disorders, but not in all of them, that this feature is consistent along the entire length of the streamline. That's the big assumption. Okay, so we used this and applied it to first our MT-on data, then we applied it to our MT-off data using the same set of streamlines that we reconstructed first using tractometry, okay? Tractography. So then we'll get two connectivity matrices. In the first, it's the, amount of signal attributed to each tract in the MT-on, amount of signal contributed to each tract in the MT-off. And then at the connectivity matrix level, we compute the MTR, and that becomes the MTR, so the magnetization transfer ratio of each tract specific, okay? So now we're going to compare that to conventional tractometry, where you just take the MTR map acquired separately and you're projecting it onto the streamlines and taking the average. And look at the contrast that we're able to retrieve. This is if you do tractometry. They all look the same. They all look the same. The projector is not fantastic, but even on my slides, they all look the same. And here we're able to really start to show, for example, mainly that the pontine fibers have a much higher MTR. So this, agrees not only with our T1 data, but also with other, reports in the literature that the pontine fibers are more myelinated. Then, of course, the cortical spinal tract, which also has a higher T1 value than some of these, connections from the cingulate to the thalamus. So, really enhancing our contrast, by improving here the specificity of the microstructural features of our tracts. And that's really important because if you want to start simulating what the impact of myelination has on functional connectivity in your brain, well, you need to be able to measure it. And right now we're just giving them a bunch of data with no contrast between the tracts when it is there. We just have to measure it appropriately, okay? All right, so this is again just to kind of show the results with tractometry. So again, that we're enhancing the contrast between different tracts in the brain, and also that in some cases, which I think is interesting, the contrast is actually reversed, right? Okay. So now just looking at this a little further using, a connectivity approach. Here we have MTR using the conventional way of tractometry, did it for B value of 0 and a B value of 1,500 just to compare apples with apples, okay? But this is still the conventional approach, and this is our new approach. You will see a difference between these two a little bit, shown here between the peaks, and that's because as soon as you have diffusion, you're kind of eliminating the MT that's happening in areas where you have, unrestricted diffusion that's happening. So it's becoming a little more fiber specific anyways. But you see how this distribution for tract-specific MTR becomes much, much broader. Okay, now projecting this onto the cortical surface. So this is a little tough to just walk you through this. What we have here is that every node basically has the mean MTR of all of the edges that is connected to that node. Okay, so it's kind of a summary, measure here. And we're looking at that for the conventional and tract specific approach. And you can, of course, it's kind of hard to see here, but you have a slightly better dynamic range again in your tract specific. I'm just windowing them differently now so that you can, really highlight the contrasts. And generally, the features hold, right? Which is good news. But there are, you're already taking an average across all the edges of each node, right? But still, there are some areas that really stand out as being different between the two techniques, right? So even when you're at the group level and you're averaging all these subjects, there are differences between the two, really highlighting the fact that we need to take this into account when we're doing group studies that look at, functional connectivity and how we can improve them. Yes, one thing I wanted to point out is that the primary areas here have a lower MTR. I told you earlier this morning that they were higher. That's because we're not looking at the same thing, okay? This morning, I was showing you maps of intracortical myelin. Myelin's actually in the cortex, in those primary areas, it's higher. If you look at the average myelination of tracts that are connected to those areas, it's lower. Okay, so we're not looking at the same thing. We were a little puzzled when we looked at this. We've looked at other data, from our collaborators, completely different data sets, and they have seen the same thing. And this is not only using our new technique, but also using conventional tractometry, applied here to MTR, applied here to MTSAT, completely different data set, and they see the same things. Right? And this is in contrast to what we see if we just looked at the cortical data. So interesting trends that we need to take into account. Okay, so that's really, I'm still past, but I think it's because I started late.
No, we started.
Okay. But still to keep you on, try to get you back on schedule so you can enjoy your lunch. So these are the different techniques. Yeah, just a quick summary of them all. So conventional tractometry, what's great about it is that you can apply it now to the multimodal data that is publicly available, right? And I really believe in reusing data and in making the most of the data you have. So we can do better, but it's still good. So still use it, still incorporate it into your models, right, of brain networks, because I think it can really have an effect. But just understand the limitations, okay? And if you can, improve on it. We have two different techniques that we showed today that are available to the community. And this one is much, much easier to use. This, will work with tools that we have now. This one, we have all the pipelines and everything available online. This one takes 13 minutes, 7 minutes. This, you can look at variations along a tract. This is a global approach. So they each have their strengths and weaknesses, right? But I think it depends on the application that you're interested in. So I'm going to stop here because the data, the next steps, my PhD student is still working on. So it was a little too early to show you today. But we are really excited because we have been acquiring this data in, to look at neurodevelopment, but also in collaboration with Sébastien Jacquemont, actually, who's at Saint-Justin, also in people who have genetic mutations that increase their risk for autism and schizophrenia. So these are people where you look at their brain images and they look fine. But we know that there's differences in functional and structural connectivity, and people haven't been looking at the microstructure. And so this is where we want to be able, for example, to really capture differences in, the caliber of the tracts, the myelination of the tracts, and see whether we can actually predict the changes in functional connectivity that have been previously reported in these groups. So, stay tuned, some exciting applications coming soon. And I'd be happy to take any questions. Of course, wait, my last slide, that's super important. Thank you, of course, to my lab, but a few people who've been really working on this are Mark and Wenda Liu, who've done a lot of this work. The 7T people who I mentioned at the very beginning are Chris and Sejad, the MR unit who helps me in everything that I do at the Neuro, and a few key collaborators as well. So, Thank you.
Okay, so thank you very much for this very nice presentation. And then let's just go ahead for the question. Christophe?
Thanks, Christine, for the great talk. It's very interesting. I have two questions. Actually, I was wondering, like, we are working on the functional side, and a part that really interests us is regions where we have a higher number of connections from the gray matter, which we call the hubs and the connector hubs. And they have very specific properties, specific metabolic properties. And I was wondering whether you use those techniques to try to disentangle a little bit what's happening in what we call the hubs, or what a few years ago it was being called the rich club, or things like that. So that would be for one question. And the other questions would be like the sensitivity of those techniques when we are going into pathological cases. And the one I'm more interested in is epilepsy, where we have a lot of malformation between the gray and the white matter. And what could be the impact? Are those techniques supposed to be robust? I don't know if you try that with Boris, for instance. Or...
Okay. So, I mean, for your first question, we started looking at that with our conventional tractometry approaches, and we found that we didn't actually have enough contrast to really go that far into that question. So we've, these data sets now we have on enough subjects that that's kind of our next step with WinDOT. So I'll get back to you with regards to that. Interestingly, we started kind of applying a lot of these techniques of graph theory to QMRI annotated connectomes, kind of directly, and the interpretations are really different. It's hard to, to say what is a rich club in a myelin annotated connectome. So I think, we're kind of changing our approach and just identifying the rich clubs as we usually do, and we're just going to look at the features of those areas. But it can be a little, confusing in the literature, the way some of the people have been using these graph theory approaches in the context of microstructure. It's not. There's no, I don't think, agreement yet on the nomenclature there. So it can be, just keep an eye out for it if you start looking at that. But it's just something we're really interested in. We have not applied this to a patient population yet. I know that Ali's been working on this, not the MR side, but just the commit side, in the context of MS and of Parkinson's, I think. So they're trying to find a way to actually deal with lesions. Okay. I don't think that's our problem in epilepsy. Like, you tell me, like, is there a lot of variation along a tract, or is it more that you're concerned about reconstructing it and reconstructing the boundaries between white and gray? Because those, I think, we can deal with, and our methods should still work. And we're really excited actually about applying these techniques to epilepsy. But
there are issues, like one of the main issues, and you have Boris is the expert on that at the neuro, is the focal cortical dysplasia, which is really a local malformations that will create blurring between the white and the gray matter. So you have lots of uncertainties here, and what could be the impact? And standard tractography tried to look at that, but I don't know, probably something can be done on those. And of course, you have variability. We've seen that an epileptic brain is getting reorganized functionally and anatomically. You get new connections, you lose some connections. And what is very interesting, several have shown that it could also be linked to the surgical outcome. Like if you remove that regions, if it has been that way connected or disconnected, that's going to impact the outcome. So it's very interesting to find out what's going on in those reorganizations.
So, I mean, you'd have to quiz Max on this, but because he's been working a lot, I think, on that near the boundary, of white and gray, and how to make sure that you're reconstructing that last little bit of your tract well. The way it works in Matrix at the moment is really, you get as close as you can, and then there's kind of this circle, that's traced with the center at that boundary, and it's kind of like a catch all the streamlines that are within it type of thing. Whereas he's been implementing techniques, oh my God, I hope I'm not saying the wrong thing here, but, to try to do better and also correct for gyral biases in tractography, which we know exist. So all of this, maybe I actually didn't say this in the presentation, but all of this relies on the quality of the tractography, of course, because the streamlines is what's being put into the system for the MT global optimization approach. But if if you're concerned about that, we can at least use the T1 approach, where if you miss that last voxel, well, maybe it's not the end of the world. Yeah. Thanks.
Thank you. Any other question? No. I have a few questions, but anyway, I'm going to summarize on. My first question is: you talk about the T1 contrast and diffusion contrast. Is there any limitation to look at the T2 contrast and the diffusion contrast?
It's a good question. So as I showed at the end of the last presentation, diffusion and T2 alloximetry have been paired before, but more to be able within the voxel to look at the T2 of the intraaxonal compartment and extraaxonal compartment, not really to look at the T2 of different tracts, The only work that I've seen on this, which is really nice, is actually using the connectome scanner. So I believe Derek Jones is the one who basically did a similar approach, but he used very high diffusion B values to just wipe out the extracellular compartment. And so then what he ended up getting using commit as well is a tract-specific intraaxonal T2. So it's cool, it's tract specific. It's only about the T2 within the axons. He's not getting the extracellular compartment. There is contrast between tracts, as I showed on some of the work by McKinnon, and Jensen. It's really nice. And what they're coming up with now, and this was just recently presented, I think, at ISMRM. So, I don't know if the full publication's out yet, but they're trying to link that to axon caliber, because it is really difficult to measure axon caliber using diffusion. We don't have the gradient power to do it. So there have been, there has been work published on this, like literally it's called ax caliber. That's the first publication on it, but it's really biased towards the larger axons. And so this would be an alternative way of getting at that really important feature, especially if you want to look at, dynamics in a neural network. To be able to know what your axon caliber is, I think it's one of the features that really modulates conduction velocity. So,
okay. Any question? The audience? No. So I think it's fine. So we can stop the question and the conference, right? So again, thank you very much for this very nice